This lesson is about solving inequalities. First, let's look at inequality symbols. Here are 4 inequality symbols, along with an equal sign. Here are the names. And let's look at some examples of how these are used. First, these are called strict inequalities because there's no equal component to them. They are strictly less than or greater than symbols. Here's an example. If I were to put a less than symbol here, would that statement be true? It turns out it is. -5 is smaller than 1. But it would also be true if I said it's less than or equal to 1. Here's another statement. Would this be true? It turns out it is. 7 is bigger than -12, but this would also be true if I said greater than or equal to. Likewise, while -8 is less than -3, it is also true that it's less than or equal to -3. This would obviously be true if I put an equal sign in here. 2 equals 2, we can't argue with that. But it would also be true if I put a less than or equal to, because it's equal. But it would also be true if I put a greater than or equal to, because again, 2 equals 2. So all of those statements would be true. Here's one more example. Think about which symbols you could put in the blank that would make this true. This would certainly be true, as would this. So our main topic here is how to solve linear inequalities. We'll talk more in a future lesson about what the linear portion of that phrase means, but here's an example of one. And our goal here is to find all x values that would make this a true statement. Here's an example. What if x were 10? I'm not suggesting you plug in random numbers for x, but just for consideration's sake, what if x were 10? Would this be true? Well, if I worked out the left side and then worked out the right side using basic math, it turns out this is a true statement when x is 10. Because after all, 68 is less than 98, making that a true statement. But 10 isn't the only number for which our inequality is true. Consider x being 11, just as a random example. If x were 11, I could work out the left side using basic math, likewise the right side, and I would discover when x is 11, this is also a true statement. Well, it turns out there's many numbers that x could be that would make this a true statement. But the interesting thing about them is that they all tend to be sort of near one another. In other words, the fact that 10 was a solution to this should have led me to conclude that 11 probably is also. And so, because all the numbers that make this a true statement tend to congregate together, we're going to exploit that, and I'll show you an algebra trick here to find all the numbers that make this true. Because while it's interesting to know that this is a true inequality when x is 10 or when x is 11, we really want to know all of the numbers that make it true, not just those two. So, here's an interesting trick. Step 1, solve the corresponding equation first. Notice the change of symbols. In other words, basically just turn the problem into an equal sign. At this point, we're going to use basic algebra. This should look familiar to you. Basic solving linear equations techniques. Pause the video if you need more time to look over the algebra. Otherwise, I'll proceed assuming that we're comfortable with those kind of basics. So we've solved the corresponding equation. But remember, that's not our goal. Our goal is to solve the inequality. So what does -5 have to do with that? Well, let's consider that as we go. Remember, our goal is to find all the numbers that make the inequality true. We've already found out that it's true when x is 10 or 11, but we really need to consider all numbers. So imagine a number line. Now what I'm going to do with that -5 is I'm going to use it to find where all of the numbers that make the inequality true are sort of hanging out, because they tend to cluster together. Here's what I mean. So you take your solution -5 to your equation and pick any number to the right or the left of it. I'll randomly pick 3, a number to the right of the equation solution. So what I'm going to do is I'm going to plug 3 into my original inequality. So let's find out if this is true when x is 3. Well, if you work out both sides of the inequality, it turns out you get a true statement. 19 less than or equal to 35 is true. And what that means is that this inequality is true when x is 3. But there's nothing special about 3. 3 is just some random number I picked to the right of my equation solution. And if the inequality is true for that value, here's a cool fact. Turns out it's going to be true for any number to the right of -5. We kind of knew that already when we found out it was true for 10 and 11. Now let's pick a number on the other side of -5. Nothing special about -7, just something I picked. It turns out when we plug -7 into the original inequality, I didn't show the algebra here, but we get this. But that's not a true statement. -51 isn't less than or equal to -55. So what we've shown here is that this inequality is false, when x is -7. But there was nothing special about -7. It was just some random number I picked to the left of -5. Turns out that implies that this inequality is false for any number to the left of -5. So far, I've discovered that this statement is true when x is to the right of -5, and it's false when x is to the left of -5. Which brings the next question, how about the number -5 itself? Well, let's test. It turns out, I didn't show the algebra, but when you plug -5 into the original inequality, you get this statement. And that statement turns out to be true. Any number is less than or equal to itself by virtue of the fact that it's equal to itself. And so that's a true statement as well. So now we know that the original inequality is true when x is -5. It's true when x is anything bigger than -5. So essentially, if x is any number in this pink area, our original inequality is true. And so, what we can do is express the answer this way. Now that may look very strange if you're seeing it for the first time, so let me explain. First of all, let's talk about the comma. That comma is a representative of the word through. So this answer is saying that all numbers from -5 through infinity, basically -5 or higher, make the statement true. Okay, well, there's our interval notation. You may also have seen it in other courses in this notation by simply saying that x is greater than or equal to -5. That won't be the notation that we use. You may have even seen it in more formal notation like this. We won't use that either. We're going to stick with interval notation. One last thought, what about the brackets and parentheses? What do those mean? Well, we'll get to that. But for now, just think of this answer, the yellow box, as saying all numbers -5 through infinity or -5 or higher will make the inequality a true statement. Now, to analyze more about what the parentheses and the brackets mean, let's consider two inequalities at the same time. Notice the slight difference between these problems. In other words, let's consider the strict inequality along with the other compound inequality. Well, in either case, if we were solving either of these inequalities, the first thing we would do is consider the corresponding equation. Notice the equal signs. Then we would do basic algebra and solve. We would then divide the number line up into two parts using the equation solution, or the -5 in this case. And then we would pick some random number to the right of it. Notice this statement is true, as is this. We would then pick some number to the left of -5, and it turns out we would get a false statement. So you see, whether we're solving the less than or equal to problem or the less than problem, the process seems more or less the same. The difference comes when you consider -5 itself. In the top inequality, when we plugged in -5, we got a true statement. -37 less than or equal to -37 is true. By contrast, on the bottom inequality, when we plug in -5, we get this statement. I didn't show the algebra here, but that is in fact what we get. The important thing being, it's false. -37 less than -37 is a false statement. A number can't be less than itself. And so -5 is the fundamental difference between these two inequalities, in that -5 is a solution to the top inequality, but it's not a solution to the bottom inequality. Either way, all numbers to the right of -5 will make these inequalities true. So now let's analyze the interval notation. Notice the difference between the two answers in yellow. Now's a perfect time for me to tell you what the brackets and parentheses mean. Mathematicians have decided that a bracket would be the symbol for inclusion. The bracket by the -5 means that -5 is included in all the numbers that work for this inequality. Mathematicians have decided also that the parentheses is the symbol of exclusion. So you can see how we used parentheses in the second answer by saying that the numbers from -5 through infinity do work, but not -5 itself. And lastly, what about the parentheses by the infinity? Why did we use an exclusion symbol by infinity? Well, mathematicians' logic is this. Infinity isn't a number. We can't include something that isn't a number, so it's logical to put parentheses of exclusion by the infinity, and that's what we always do. Let's remember that infinity is not a number. Infinity is just a symbol that reminds us that numbers go on forever. If you look at the two problems and the two solutions, I think you'll see the contrast that I was trying to provide you with here. Let's look at the same problem again, but this time I'd like to show you a shortcut. Here's a shortcut you may have seen elsewhere. Instead of turning this problem into an equation and analyzing the number line, I could just do the basic algebra to the inequality itself. In other words, I could add 2 to both sides here. Notice what happened. I could then subtract 9x from both sides, notice. And I could then divide by -2. In other words, for a linear inequality, again, more on what linear means later, you can do all the basic algebra steps that you would do for an equation to the inequality, with one small exception. Notice the reversal after dividing by -2. If you're going to use this shortcut, there's an obscure rule which states if you're dividing both sides by a negative, you switch the direction of the inequality. There's all kinds of good reasons for that, which we won't discuss here, but it's a good thing to know with the shortcut. And once we've discovered that x has to be greater than or equal to -5, that means that anything that's greater than or equal to -5 on a number line will be a solution to this problem. And once you see that graphically, you could express it using interval notation. Now this is a fine shortcut, but it only works for linear inequalities. Again, more on that later. Here's a different example. Suppose we wanted to solve this inequality. That means we want to find all values of x for which this is a true statement. I'm going to consider the corresponding equation, which turns out to have a solution of 5/3. If you want to try the algebra yourself, pause the video here and try the algebra. Here's some version of what you might have done as your algebra. The point here, though, is not to reteach equations as much as it is to see how the inequality is related. So, in order to solve this inequality, let's consider all numbers. All the x's that make this inequality true are going to be together in one place on the number line. So I'm going to use this 5/3, the solution to my equation, as my divider between the numbers that will make the inequality true and the numbers that will make it false. So just as before, I should pick a number on either side of 5/3. 5/3, by the way, is about 1 2/3. So let's randomly pick 0, which is to the left of 5/3. If I plug 0 into the original inequality, not showing the algebra here, but what happens is I get this statement. Well, -10 is less than 0. That is a true statement. But remember, there's nothing special about 0 here. 0 is just some random number I picked to the left of 5/3. But getting a true statement out of the inequality means that not only is this inequality true when x is 0, random number, it's true for any number to the left of 5/3. Now let's pick a random number to the right of 5/3. 5/3 being 1 2/3 means I can pick 2 as my random number to the right. Well, if I plug 2 into my inequality, again not showing the algebra, I'll get this statement. But that isn't true. -6 isn't less than -8. Therefore, I not only know that the inequality isn't true when x is 2, I more generally know that that inequality isn't true for any number to the right of 5/3. So now I've discovered that everything to the left of 5/3 will make our inequality true. Everything to the right of 5/3 will make it false. So what about 5/3 itself? Well, let's test 5/3. I'm going to take the inequality and plug in 5/3 for x. Now I worked out both sides on scratch paper, and I got the same number. Therefore, this is a false statement, because a number can't be less than itself. Now, if you want to avoid all this fraction work, here's something to think about. I would have known that 5/3 failed to make the inequality true. I would have known that 5/3 is false even without all the ugly fraction work. Here's my logic. 5/3 was a solution to the equation. What does that mean? That means that if x is 5/3, these two quantities are equal to each other. That is what an equation is. But if those two quantities are equal to each other, when x is 5/3, then so are those two quantities. So I would have known, even without getting -20/3 and going through all the trouble, I should have known that those two quantities in the brown boxes would have been equal to each other when x is 5/3, and therefore false, because a number can't equal itself. So what I've discovered so far is that if x is any number to the left of 5/3, the inequality is true. But if x is 5/3 itself, or anything to the right, the inequality is false. Since our solution is always what makes the inequality true, here's my interval notation. Notice I use the parentheses of exclusion at 5/3 because 5/3 was not a solution to the inequality. Notice I use the parentheses of exclusion by the -infinity because I shouldn't include something that isn't a number. That wouldn't make a lot of sense. And again, I use the comma as the through. Be careful not to put this as your answer. It's not proper to put 5/3 through -infinity, which is a very common way to express this by most students who don't know otherwise, because there's a convention in interval notation that we always go left to right. In other words, -infinity is to the left of 5/3, so I'm going to list it first. If you wrote 5/3 comma infinity, -infinity, teachers would know what you meant, but you'd still be wrong, because that's not the way interval notation is written. That concludes the lesson.